So here we see the functions palette on our FPGA, and we see that within the programming palette there's a timing palette, and in there we've got a loop timer, wait, and tick count function. So the loop timer Express VI, we're going to use that to implement loop rates. We're going to use the wait Express VI to create delays between events, and we'll use the tick count Express VI for benchmarking. So here we'll talk about implementing loop execution rates using the loop timer Express VI. So the loop timer Express VI, when you place it down, it's going to wait the value you specify and count between loop iterations. And that's essentially how it's going to control the period of the loop and the frequency of the loop. So the way that you would use it is you would place the loop timer Express VI inside a loop. And then that way, by using this function, or the loop timer Express VI, you're going to be able to perform I/O operations at a specific frequency, and you'll be able to control the loop execution rate. So we'll take a look at a block diagram to see how this actually works. So when you double-click that loop timer Express VI, you get a configuration dialog. And in that configuration dialog, you're able to specify the counter units, and you're also able to specify the size of the internal counter. So let's talk about the counter units first. So one unit of that counter you can use is you can have it in units of milliseconds. You can also get it in units of microseconds, or you can also use ticks, which is clock cycles. So if you're using ticks, that's one way you can get nanosecond resolution, and we'll talk about that more later as well. The size of the internal counter, so you can select 8-bit, 16-bit, or 32-bit, but the reason why the size of the internal counter is important is that it determines the maximum time a timer can track. So to save space on the FPGA, you can use the smallest size of internal counter that you need for your application. So it's kind of a trade-off. If the size of the counter is larger, then you're going to be able to keep track of more time, but at the same time it's going to take up more space on your FPGA. So when you're choosing this, think about what's the maximum amount of time you'll need to keep track of, and then select the smallest size that can accommodate that. And we'll give examples of how these 8, 16, and 32 bits actually relate to time later on. So let's take a look at this block diagram, and we'll talk about and walk through how the loop timer is actually executing. So the very first iteration of this loop, we're going to get to the loop timer, and what it's going to do is it's going to record the current time as the initial time and immediately execute the code in the next frame. So the very first iteration, the loop timer doesn't take much time to execute at all. It just records the time, and then it goes to the next frame in that sequence structure and executes whatever code is in there. So let's say that code executes, and now we're going to the second iteration of that while loop. So in the second iteration of this while loop, the loop timer is going to add the count that you specify there to the initial time and wait until that count has elapsed. So if the count was like 10 milliseconds, it's going to wait until 10 milliseconds has elapsed since that loop timer was first called. So once that's happened, it's going to go on to the next frame of that sequence structure and execute the code again. So on the subsequent iterations, the loop timer is always going to be comparing how much time has elapsed based on the first time it was called. So if I put 10 milliseconds, it's going to make sure that that loop is executing at a rate of once every 10 milliseconds based on the original time of that first call. So let's talk about a caveat real quick. So what happens if the code in that second frame takes longer to execute than the specified loop rate that you've done in that loop timer? So if we take a look at this, let's say the loop timer is set for 10 milliseconds. Okay, so let's say that executes, and then we go to the next frame. In the next frame, let's say that code happens to take 15 milliseconds to execute, so it's taken longer. On the next iteration, when we get to the loop timer, it's going to notice that, the specified time that I put of 10 milliseconds has already passed, and we've run over that. Well, the loop timer is going to record a new initial time right away, and then it's going to go immediately to the next frame, and then it's going to execute code. So if for some reason in that loop, the loop timer misses its expected time, it's going to automatically record a new initial time and then start over. Okay, so in this slide we see some actual numbers that are associated with the size of that internal counter. Okay, so let's take a look at the right-hand side. Let's say we've set the units to milliseconds of our internal counter. So let's see what happens if we use an 8-bit counter. If we have an 8-bit counter, that means our counter can basically go from 1 milliseconds to 256 milliseconds. If we've gone over 256 milliseconds, then we're going to start rolling over, and our timing is no longer going to be accurate. So let's say we need our timer to go past 256 milliseconds. Well, we would need to make a bigger size for our internal counter. So let's say we increase the size to 16-bit. Well, now that counter can go from 1 millisecond to 65 seconds. If we raise that internal counter size to 32-bit, then we can go from 1 millisecond to 49 days. If I choose microseconds as my unit instead, then we see the ranges there. So for 8-bit, it goes from 1 microsecond to 256 microseconds, and at the largest size, the 32-bit, it goes from 1 microsecond to 71 minutes. So this is a good way to kind of at least get a gauge of what the size and unit, how it affects your loop rates, and when those things are going to actually roll over. So let's take a look at tick period. So if you're using units of ticks, then what that's going to represent is each tick is going to represent a clock cycle. So if you are using the default 40 megahertz FPGA clock, that 40 megahertz corresponds to a tick period of 25 nanoseconds. So if we're looking at that left column over there, each of those ticks represents 25 nanoseconds. So an 8-bit counter, if you're using ticks and a default 40 megahertz FPGA clock, it's going to range from 1 tick to 256 ticks, which if you convert that to nanoseconds, that's actually 25 nanoseconds to 256 times 25 nanoseconds. So if you need to get nanosecond resolution, you'll have to use ticks for your units. So you can see with your units, you can now have nanosecond resolution, you can have microsecond resolution, and also millisecond resolution.